x equal to 3.30 and a equal to 3.120. Okay, now you see, here we have 3 zeros. Maybe you say, okay, it's equal to 3. Okay, what's the difference between 3 and 3.000? Can you tell me? Or can you ask by yourself, right? Okay, actually, in mathematics, they are same. In theory, they are same. But for computer, the zeros also represent the different meaning because it means we have precision. It's okay for you? Okay, 3.000 or 3.0, we know they give different precision, accuracy, different accuracy. It's okay for you? Okay, and we have the difference, the absolute error, we know it's just the minus 0.1. Now you see, we have a negative error, right? Because here, just the absolute error, not absolute value of error, okay? So this is absolute error. And for the relative error, because here we know the exact x, so we can use directly. Okay, so here we obtain like a minus. Actually, it should be almost, because close to minus 0.3333, right? We take 3 threes, multiplied 10 to minus 1. Okay, this is a relative error. Okay. Now let's consider second case. For another two numbers, x equal to 3000.00, and if we write like this, 0.300 multiply 10 to 4, it's okay for you? 1, 2, 3, 4. Okay, so the decimal place is here, right? And a is 3100. So we also use this form by 1, 2, 3, 4. It's okay? So here 0.310 multiply 10 to 4. Now let's consider the absolute error again. So the difference is minus 0.1 multiply 10 to 3. It's okay? 10 to 3. 10 to 3. Now let's compare the two cases. Here 0.333. Here 0.133. 100. Sorry, 00. Here we also have 3 zeros. The difference from this x to this x, the difference is a different decimal place, right? Okay, so the absolute error is different. However, if we consider the relative error, see, here is minus 0.1 multiplied 10 to 3, then the denominator is 0.3 multiplied 10 to 4, right? Okay, now you see, the relative error is same as this one. Of course, here it's better to use approximate, right? You see, what is mean? Because the power is also same, right? So that means, okay, the relative error is independent of the decimal place. It's okay? It means the relative error is independent of the decimal place. But absolute error depends on the decimal place. You see, different absolute error. Okay, in conclusion, this example shows that the same relative error occurs for widely varying absolute errors. As a measure of accuracy, the absolute error can be misleading, and the relative error more meaningful because the relative error takes into consideration the size of the value. So usually, okay, when you publish paper, okay, if you need to compare the numerical results, usually, okay, we use relative error because we consider the size of the value, right? The real exact value.